Welcome back. We're going to change gears now and look at some computational issues, practical issues with computing with matrices. I'm going to start off by talking about computing eigenvalues. This is a hard problem, computing eigenvalues, it's important. It's hard because if you have an n by n matrix, the way you compute the eigenvalues, well, the natural way is you write down this polynomial of degree n, and you need to solve it, and that's, for big N, is extremely hard. And it's also very unstable, which is another way of saying that it's hard. And that is to say, small changes in the matrix can cause big changes in the eigenvalues. And so, for an example of that, let's consider this matrix. Suppose you had all zeros on the diagonal, ones below the diagonal, and zeros everywhere else except for some small number here in the upper right-hand corner. So if this epsilon were 0, then, of course, 0 would be the only eigenvalue of this matrix. But suppose epsilon was tiny. So let's say n was 100 by 100 matrix. And suppose epsilon was 10 to the minus 100th. That's an absurdly small number that will never actually come up in practice. It's a decimal point followed by, well, not 100 actually, 99 zeros and a 1. Ridiculously small. And that tiny little perturbation causes the following. The equation becomes lambda to the 100th is equal to 10 to the minus 100th. And one of the solutions of that is lambda is equal to 10 to the minus 1, which is to say 1/10, 0.1. And 0.1 is huge compared to this perturbation. It's 10 to the 100th times bigger. So this tiny little perturbation caused a huge change in the eigenvalues. So anytime that happens, the computation is difficult because it's very sensitive to errors. Okay, I'm going to talk about two techniques today. One of them is called the Gershgorin disk method, and I'm just going to call it generally the disk method. And the idea is the following. Suppose you have a matrix A with its diagonal entries, and suppose the entries of the matrix not on the diagonal are small compared to the AIIs. The AIIs are large compared to the other matrix entries. Well, then the matrix is sort of kind of approximately diagonal, so you might think that the eigenvalues of the matrix are actually close to these numbers on the diagonal. So here's an example. Suppose you had a matrix like this matrix with 2's on the diagonal and 0.1's off the diagonal. Well, it turns out that the eigenvalues of this matrix, well, they're not 2, but they're close. They're 2.1 and 1.9. And that's what the disk method does for you. It enables you to estimate eigenvalues very easily. So here's how it works. So let's take, everything's about complex matrices here. So let's take an n by n complex matrix, and I'm going to focus here on the ith row. So the ith row is AI1 up to AII up to AIN. And I'm going to single out the ith row, and I'm going to define the number Ri to be absolute value of AI1 and so on, the sum of all these numbers, up to absolute value of AI minus 1, and I'm going to skip the diagonal one, all right? Skip the AII term, but include all the others up to absolute value of AIN. So that is to say, Ri is the sum of the absolute values of the numbers in the ith row, not including the diagonal term, not including AII. Okay? So that's a real number. It's the sum of a positive number. It's the sum of these absolute values. Non-negative, of course. And define the ith disk to be the disk in the complex plane of radius Ri centered at this diagonal entry AII. Okay? So AII is a complex number. Plunk it down in the plane. Here it is. Draw a circle around it of radius Ri. That's a disk in the complex plane. Okay? So that's the setup for the disk theorem. We have the ith disk di, and I'm going to draw a typical example here. Here's the first disk, and here's the second one, and maybe here's the third one. They're allowed to overlap. Okay, they're more or less random disks somewhere in the plane. And here's the theorem. The result is that every eigenvalue of this matrix is contained in at least one of these disks. So this gives you a constraint. It tells you where to look for these eigenvalues. They're contained in this region, which is covered by these disks. Okay, so we have a 5 by 5 matrix here, so the 5 eigenvalues are somewhere in these regions. So they're somewhere in these regions. Now notice I'm not saying that every disk has an eigenvalue in it, just that all of the eigenvalues are somewhere in these disks. So this gives a lot of control over the eigenvalues. Qualitative control, and the smaller the RIs, the better control you have over the eigenvalues. All right, now there's an important second part of this theorem, which I will now explain. So let's say the picture looks like this. We have these overlapping disks, and over here we have, let's say, k disks, which are all connected to each other. And then over here there's a disjoint set of n minus k disks, which are all connected to each other. Well, even though I can't tell you that there's an eigenvalue in each disk or anything like that, when you have these two separate regions like this, something very neat happens. And the result is that when this happens, this first region, which is made up of k disks, has to contain k eigenvalues. And this other region, similarly, has to have n minus k eigenvalues in it. So again, they can be anywhere. There have to be 3 in this first region. They can be anywhere in that region, all in one disk, all one in each, or whatever. And there have to be 2 in this other region over here. That's the result. Now, you might have noticed that on the previous slide I didn't quite satisfy this, so you should go back and look and see where there's a mistake on the previous slide about where I put these red eigenvalues. Okay, so let's look at an example. This is a very important special case. Suppose all n disks are disjoint. Okay, so they're all separate like this. Okay, then what happens? Well, by repeatedly applying this theorem, we conclude that every one of these disks has an eigenvalue in it. And in particular, it has to have n distinct eigenvalues and is therefore diagonalizable. So that's incredibly cool. It's a very cheap way to prove that a matrix is diagonalizable without actually computing any eigenvalues. Okay, so that all seems like magic, but it's not. It's actually very easy. Let's see the first part. The second part is a little harder, but not too bad. So the first part, I'll restate it here. So we have this matrix A, and these n disks, and lambda is an eigenvalue of A. I'm saying that lambda has to be in one of these disks, at least one of them. All right, why is that? Well, so here's how it works. So lambda is an eigenvalue, so there's some eigenvector, AV is equal to lambda V. And let's write V as x1 through xn. I have no idea what this eigenvector is, or this eigenvalue, but it exists. And whatever it is, it has some biggest term, xi. That is to say, absolute value of xi is bigger than or equal to all of the other absolute value of xj's. Okay, there might be more than one. There could be several that are equal, but just pick one of them. And I'm going to look at the ith coordinate of both sides of this equation. So on the left-hand side, the way I'm going to get the ith coordinate is when I multiply the ith row of the matrix times the vector. And on the right-hand side, I'm just going to multiply lambda times the vector. And so on the left-hand side, I'm going to get the sum of the a's times the x's. ai1 x1 plus dot 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 ain xn. And on the right-hand side, the ith coordinate is simply lambda xi. All right, what good is that? I don't know. Let's see. So we have an xi on both sides of this equation. So let's move it over to the other side. So I put a hat to indicate that I remove that term. And on the right-hand side, I get lambda minus aii times xi. Okay. Now again, I don't know lambda. I don't know the xi's. But let's see what we can conclude from this. Well, I'm saying something about disks and distances and things, so the obvious thing to do is to take the absolute value of both sides of this equation. I'd like to switch the sides, so on the right-hand side I'm going to move it over and say absolute value of lambda minus aii times absolute value of xi, and that's equal to the other side, which is the sum of these guys. And by the triangle inequality, you can replace that with absolute value of ai1 x1 plus dot 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 ain xn. Okay, so that's an inequality I have now. And I'm going to take this absolute value of xi and move it to the other side. So I conclude that absolute value of lambda minus aii is less than or equal to absolute value of ai1 times this ratio, x1 over xi, plus absolute value of ai2, and so on, all the way up to the absolute value of ain, absolute value of xn over absolute value of xi. Okay, so let's see. What good is this? Well, notice that all of these ratios, absolute value of xj over xi, these are all less than or equal to 1, since xi is the biggest one. So all of these numbers are less than or equal to 1. So I can replace them with 1 in this inequality, and this right-hand side is less than or equal to the sum of the absolute value of the aij's, not including the ith one, because I moved that to the other side. Okay, we're basically there. I'm telling you that the absolute value of lambda minus ai, well, this thing on the right-hand side is ri, that number ri. So I've concluded that the absolute value of lambda minus aii is less than or equal to ri. That says if you draw aii and this ri, that lambda is closer to aii than that. That is to say, lambda is in this disk. That's it. You get a lot of mileage out of this very simple computation. So let's look at a couple of examples. So this example I did before with 2's on the diagonal, this R1 is just 0.1, and R2 is also 0.1. And the two disks in this case coincide. They're both centered at 2 with radius 0.1. And in this case, both of the lambdas are actually on the boundary. We were getting 1.9 and 2.1. They're both in that disk. Now, if I change the problem a little bit and I had a 2 and a 4 on the diagonal, then the two disks look like this. They're the same radius, but they're centered different places. Now, you have to have one eigenvalue in each. And in fact, the two eigenvalues turn out to be very close to 4, 4.005, and very close to 2, 1.995. Okay, and let's look at one last example. Suppose you had 1 and 1.2 and 3 down the diagonal. And I'm not going to specify what's off the diagonal, but let's say that these RIs, say, turned out to be each less than or equal to a half. I'm just sort of making this up, but you could certainly imagine that. And then what would the picture be? We have these 3 points, and the 3 disks look like this. The one over here and these 2 overlapping ones here. So that says 2 of the eigenvalues have to be in this region, and 1 of them is close to 3. All right. I'm going to turn next to another technique for computing eigenvalues. It's using powers, and it's a very simple idea. Suppose you have a matrix A with a bunch of eigenvalues, lambda 1 through lambda n, and suppose lambda 1 is the biggest, strictly biggest. Its absolute value is bigger than all of the others. Well, we've seen that if you repeatedly apply A to any vector, it's going to approach this lambda 1 eigenvector. We've seen these pictures. It's all the other terms go to 0, and you converge to that eigenvector. So that tells you how to compute the eigenvalue approximately. What you do is start with a random vector, v0, and let's say the first coordinate is a0. Then apply a to it, and you get some first coordinate a1, and then another time a2, and so on. And after k applications, you get ak, and another one you get ak plus 1. You compute these numbers, and you look at the first coordinates of all of these vectors. Well, when k is big enough, this is close to the lambda eigenvector. So this avk is approximately lambda 1 times vk minus 1. Lambda 1 times vk. And lambda 1 times vk is, well, it's lambda 1 ak. And so I conclude that this ratio must be approximately lambda. I conclude that lambda 1 is approximately ak plus 1 over ak. And in fact, lambda 1 is the limit as k goes to infinity of this ratio. Okay, so that's not too hard to compute, and you can do it as far as you want until you get the desired degree of accuracy. So this gives you a technique for approximating the largest eigenvalue of a matrix. Well, only in the case when there is a unique largest one. There's one that's strictly larger than all the others. And it's not apparent from what I've said here, but the convergence of this method is incredibly slow. So it looks kind of nice, but it's actually kind of slow computationally. So what we're going to do next is to look at some enhancements of this which will improve the convergence. And I'll get to that next time.